Hi, folks. So when we covered F2 in class, we didn't quite get through all of the lecture slides. And that wasn't critical to the large class as a whole, but I did think that the last segment that we didn't cover might be useful for some of you putting together your final projects and trying to see how to make sectors that say allow a natural resource to interact with human activity that might interact with policy and then allow you to change the policy. And that was handled in this chapter 9 in this Morecroft text. And so that's what I wanted to cover here. And basically what we're talking about is we've currently modeled a simple harvested fishery where we've covered the growth dynamics of the fish. But right now we have left the ship dynamics, so how the number of ships change, be exogenous to the system. And so it's a parameter that we set once and we run a whole simulation, or maybe we pause the simulation and then set the parameter up or set it back down, but we don't, the dynamics are not internal to the system. And so we would like to make the ship dynamics endogenous to the system. So we know how fish grow, and so we'd like to figure out how do ships grow. All right, so what was done in Morecroft was to create this additional little sector that represents the fishing industry. And this sector has got a number of ships at sea over here, and it's a dynamic variable, so it's a stock variable. So we want the ships at sea to be able to change automatically as the simulation is running. And so you can imagine then how are we going to model that? Well, we can kind of think that the ship owners, or maybe the industry owners, have a desired fleet size, which is down here. And so this desired fleet size is a number of ships that they would like out there. And so there is going to be some delay that represents how long it takes to buy these ships and get them ready to deploy and then deploy them. And so you can basically imagine there's a current number of ships that are out there at sea. There's a number of ships that the owners would like, and they are going to look at the gap between those two, and then they're going to make investment decisions. And so they might purchase, or maybe they want to sell, so they want to get rid of some of their ships. And that will affect the flow into the number of ships. But whatever they do, deciding to sell their ship or deciding to buy a new ship, it's going to take time to adjust. And so you get this time constant for this system. So basically this loop right here represents a type of a first order smoothing delay with this time constant here. So this is just like the toilet tank model that's kind of been built in here. So if we just left it at that, then whatever you set the desired fleet size at, just like the toilet tank, it would come up to that desired fleet size and sit there like a constant. So it'd basically be a parameter there. So what we're going to introduce to allow us to model the decisions of the ship makers changing as they get feedback from the fishery and feedback from the policymakers is we're going to create kind of a psychological parameter called propensity for growth. And this is right now in this kind of sector perspective, looks like an exogenous variable that you kind of set, but we are going to make this propensity for growth interact with the fish population and again, policymakers and those sorts of things. So you can think of this as a kind of per ship birth rate. It represents how the ships will grow or shrink over time. And so we are going to make this a little more complicated, this propensity for growth, by expanding its connections. And this is going to be, there's going to be a slider called normal propensity for growth. And you can think of this as like ahead of time, they said, well, based on our historical data, we expect to have to buy 5 ships a year. So that's our normal propensity for growth. But we're going to allow this to get modulated over time based on how successful the ships have been out there in the fishery. So if we think about it, we've got up here, we've got fish density, which is going to come from our normal fishery model, which is over on the side. We're already done with that. That's our standard growth model, which is a growth model of the fishery. We've got that. And that's going to set up a fish density. That's how the fish are going to enter into that. Now, we could build a lookup table right here, and that lookup table represents, based on the density, this is going to affect, it's going to be a modulating factor on how easy it is for each ship to find fish. So each ship has a normal catch per ship, that's over here, the normal catch per ship, which basically means under normal situations, under normal densities, each fish is going to go out every day and be able to find, 30 fish. But if the density of fish becomes really high, then maybe actually they go out and they find 40 fish. Or maybe if the density becomes very low, they go out and they find 20 fish. So there's some relationship between the actual fish density and the actual catch per ship. And so we set kind of a normal catch per ship, and we have a lookup table that you can imagine this going from, say, -1 to 1. So the fish density goes in as the independent variable on the x-axis. So you've got fish density is going in here. And maybe on the y-axis, you've got some modulating factor, which goes all the way up to 1, and maybe it goes all the way down to -1. And that is going to get multiplied by the catch per ship. So, and this is how one way to set it up. The way they've set it up in the book is down here in this lookup table down here. It looks like they've set it up so that the modulating effect is never negative, but it's so this -1, it doesn't go all the way down to -1, it only goes to 0 here. And so a fish density goes in and you get a value between 0 and 1 that comes out. And that's what's being set up down here. That's what this lookup table is down here. So this, as the fish density changes, it changes the catch per ship, which ultimately will change the catch if you multiply that by the number of ships that are available. But it affects the decision making as well, because each boat is going to radio back and tell the boat owners, I only found 5 fish today, I only found 10 fish today, or I found 30 fish today, or 40 fish today. And that is going to modulate the propensity for growth. And so that is captured by this lookup table. And that lookup table basically takes as an input the number of catch per ship. And as an output, it then has a scaling factor. Let's say it goes from -1 to 1. And that is going to then scale whatever that normal propensity for growth is. Say it's 5 boats per year. Well, if we're getting a lot more fish than we expected, as captured by the lookup table, then the actual propensity for growth might not be 5 ships per year. Maybe it will be 10 ships per year or 20 ships per year. But if we're getting less than our normal catch per ship than we kind of expect, then maybe our normal propensity, where it might have been 5, will actually go down to 4, 3, 2, or maybe we won't buy anything this year. So we are trying to wire in the success in the fishery with the investment decisions about the number of ships. So that's the goal here. So we're saying as the catch per ship decreases, the propensity for growth can even become negative, causing the fleet size to shrink. So that's captured in this lookup table down here. This is effective catch on propensity for growth. So there's this lookup table right here. And so you can see that the inputs are the numbers on the left. And you can see that for low densities, the propensity for growth actually becomes negative. But for high densities, it goes all the way to 1.0. And that propensity for growth gets multiplied by the normal propensity for growth in the propensity for growth here to give us the actual propensity for growth. That's what's going on. So we've basically set up a balancing loop. As fish density increases, you get the same effect on catch per ship. You get the same effect on propensity for growth. So as fish density increases, ultimately the propensity for growth is going to increase, which is going to increase the number of ships per sea, but that is going to decrease the fish density. And so that decrease in fish density ultimately is going to slow this whole process down, so the number of ships should level off. The other way around to look at it is if you had a decrease in fish density, that's going to decrease catch per ship, which is going to decrease enthusiasm, which is going to decrease the ships at sea, which hopefully then will increase fish density, which will then slow that down as well. So we have this balancing loop. And so we've now managed to make investment decisions endogenous to the model. We have modeled the psychology of those making decisions about how many ships to buy and how many ships to sell. So that we put all of that together and we get this combined kind of two-sector model. So we've got our old growth model up here, and then we've got our now industry model down here. And because investment decisions are endogenous to the model, we can now get long patterns, not just short patterns. So before we would say, set the number of ships and see how things went. Well, now we can actually see how things go over long periods of time because we actually have modeled the human decision-making internal to the model. So we can let the model go and it will change the number of ships over time. So as we can see here, the number of ships stays, so 4, so ships at sea, it stays constant for a while. But and so as it's staying constant for a while, then what's happening, because is that the declines here in the fish stock end up creating an increase in the new fish per year. That's this 2 here. And the increase in the new fish per year is going to end up generating more catch. So that's what's happening here. And that increase in catch is going to then trigger growth in the number of fish or number of ships on the sea. And so that is going to trigger all these things to start rising. But as the catch increases, eventually the catch will increase to a point that the fish stock will end up decreasing so much that the regeneration rate, or the new fish per year, goes over its tipping point. And at that point, the regeneration rate, the new fish per year, will start decreasing. And as it starts decreasing, then you'll notice that the subtle decline in the fish stock becomes a rapid decline. And that rapid decline in the fish stock isn't quite sensed by the ships yet. And so the ship catch, so here's catch per ship, it has so far been high, and it might start to decline around this tipping point, but it stays high enough that the psychology of the and actually the total catch ends up continuing to rise. And so even though the catch per ship is coming down, the total catch is continuing to go up. And so investment decisions continue in this model to rise. And you don't end up getting a decrease in catch per ship that is sufficiently low to cause investment decisions to turn and decrease until basically it's too late. And they decrease so slowly that you end up getting a collapse to extinction in the fishery. So we see over this long behavior over time, we see a number of really cool dynamics, kind of like in the oil example with Saudi Arabia and all that. So now we can simulate long batches of time and watch psychology unroll. So that's kind of was our goal here. So the crash in this simulation is actually a good sign. It's not good for the sustainability of this simulated fishery, but that demonstrates that our fishery is able to simulate realistic scenarios that we would like to study. So that allows us to say that our simulation generates the type of phenomena that we're interested in the real world, which means that we can now experiment with the simulation, and maybe that experimentation will give us insight into what we can do in the real world. All right. So, but how are we going to intervene in the real world? We need to model our intervention in our simulated model. So what we're going to do is we're going to add a little bit more to the simulated model. And so we now we need to model scientific information coming into the fishery, about the fishery. So we've got the real fishery, which is kind of hidden. And the real fishery has a real fish density. And there is some sort of optimal fish density, which we don't know what the optimal fish density is, but we need to figure that out. And then that will go into the deployment policy, which will affect how many ships will end up being deployed. And all this is going to be modeled by our estimation of what the fish density in the fishery actually is. And so we have to model our kind of uncertainty in this as well. So now things blow up and they become a little bit bigger. We have our old fishery up here on the left. That's kind of one sector. We have our industry model down here. And then we've got, this is sort of the scientific model here, which represents how we are estimating the true fish. We don't know the true fish density because it's under the water. We can't tell it's there. So we need some way to estimate that. So let's zoom in on that region right there. And so we've got our real fish density, and we've got a time to estimate the fish density. We have an estimated maximum fishery size. And so all of that, and then we've got some sort of assumed optimal fish density. And so we use some formula which gives us an estimate on our certainty of our estimates of the fish density. So there's a real fish density out there, and whatever the real fish density is this, we are going to get some confidence interval on our estimated fish density, and we're somehow modeling that uncertainty in this estimated fish density. And then if we have an assumed optimal fish density that hopefully science has told us, we can then calculate some sustainability index based on how much we estimate is in the fishery and how it compares to the optimal fish density. And then that sustainability index is going to drive our policy recommendations down here. So this whole section up here represents the scientific process of inferring how many fish are out there and suggesting to the industry or to policymakers, how much additional fishing is sustainable. Now, once we make those recommendations, we are going to have a slow and imperfect enforcement policy. We say we need to reduce the number of ships, but it's not necessarily going to happen instantaneous. So there's a total number of ships that are out there, and that total number of ships and our recommended ships. So based on the total number of ships, we can compare to the estimate from our sustainability index of how much fishing can happen out there. And then that should hopefully affect the flow rate of ships so that you not only can get ships out of this stock, so you can reduce the number of ships in this stock, but it takes time to achieve compliance. And so that time is going to mean that even though we might say we need to reduce the number of ships right now, it just takes time, and so there's going to be some lag, some delays. And we can even model the effectiveness of this. And so this so-called effectiveness of fisheries management regime, that's kind of a euphemism for saying that there might be some in the industry that totally ignore our recommendations. And so we can actually model how much of these recommendations actually count in the investment decisions. So we can put that all in the model. Okay. And so all of that gets, so we've already had our ship operations. This is what we built last time. And we already have our fish population, what we built last time. And so that whole model goes in, and here's all the formulas for it. And now we have a complicated model that is modeling the fish growth, it is modeling the ship growth, and is modeling the scientific process and information to the policymakers and policymaker recommendations on the industry and how well the industry responds to that. So these three sectors all interacting. And what you get out of that is a lot of really interesting dynamics. And so we get up here these oscillations, and these oscillations are actually introduced by the regulatory process itself. So we now have a sustainable scenario rather than a crash. So we have a bunch of like micro crashes that get rescued by our policy. And that's what we're seeing played out over this long time period. So if you're to focus on like the fish stock, you can see it crashes for a while, but it ends up reaching a point where the enforcement, so you can see if we're to look down at this other set of graphs here at the bottom, we've got a fish density, we've got an assumed optimal fish density, which sets up kind of a trigger for enforcement, our sustainability index, so our sustainability index, we can kind of watch. Things are sustainable for a while, and then suddenly our sustainability index crashes. And when that is an indicator that tells our policymakers they need to kick into action and need to change the number of recommended ships at sea. So our recommended ships at sea here, when our sustainability index is high, the recommended ships at sea grows. But when the sustainability index drops, so does the recommended number of fish or ships at sea. Now the actual number of ships at sea, it's up here, that's line 4 here, it's going to grow, and its dynamics might lag behind and lag in intensity compared to the recommended number. So the recommended number kind of swings larger than the actual swings that are up here. But overall, we can see that as the recommendations move back and forth, they are affecting the actual decisions here. And that actual decisions is allowing us to move the fishery around that maximum sustainable yield. And so we can bring them up to close to the maximum sustainable yield. And even if they go over, we can whack the fishery so that they hopefully quickly can get back onto the sustainable side of that growth curve. Now, if you make the target density, so this is the assumed optimal fish density, if you make that target density too high, so this is significantly higher than the maximum sustainable yield, we see a disappearance of those oscillations. So what we're saying that is we're basically saying that if we allow them to fish the fishery down to a low density that is close to the maximum sustainable yield, we're going to get the oscillations from this other graph. And that's because we're kind of, we're playing very close to, we're in risky territory. And so if you're in risky territory, you're relying on regulation that is kind of lets things go overboard and then has to correct massively, and then lets things go overboard again and then correct massively. And so you get these huge oscillations. So this is only a marginally stable outcome, even though it's a sustainable outcome. So if you want both stability and sustainability, and also want safety margins so that maybe your parameters are not quite as sensitive, or maybe your system is not quite as sensitive to choosing the wrong set points. If you set your set points higher than they need to be, so a little more conservatively, then what you end up finding is that you never push your fishery into a point where you are flirting with or going over the maximum sustainable yield, the tipping point. And as long as you can stay on the kind of negative side of that hump-shaped growth curve, so in that growth curve, it looked like a hump here where the maximum sustainable yield was down here, and this here was the kind of safe side. As long as you keep the fishing over here, then you're not going to get these wild oscillations. You only get the wild oscillations if you go over and this maximum sustainable yield and then need a massive corrective action. And then you can go back and forth and back and forth. As long as you stay over here, you have the opportunity to keep things stable. And that's what we're seeing right here. So by setting the target density, not like here, by setting the target density to something higher, then we don't maybe get a lot of, we might lose out in the short term on economics, but in the long term, we gain on the economics because we have a greater way we can kind of count on this fishery being, staying around for a while. So there are other experiments you can do, like you can make, for example, increase the scrap rate. And so that makes it easier for fishermen to exit the industry. So you might say, I'm going to experiment with a scenario where we are going to make these fishermen or the fish industry being able to rapidly get their ships out of the water. So we're going to increase this scrap rate. And you might think that's a good thing, but what it actually does is just amplifies these oscillations, because now you get a rapid decrease in the ships, which causes a rapid increase in the regeneration rate. And then that's going to cause a rapid increase in the ships and back and forth. And so you actually get more cyclicity, so more cycles, not less. So, so if you want to get rid of cycles, you got to be more conservative. If you're okay with, if you want to be less conservative, you're going to deal with these rapid cycles. But you have to be really careful, because if you chose your set points, if you chose your assume optimal fish density wrong, then your system's going to be much more sensitive to incorrect choices here. So if the actual optimal fish density is a different level than your assumed optimal fish density, and you chose kind of the wrong side of that, your assumed optimal fish density, then you put yourself in a dangerous situation. So you open yourself up for error if you make a less conservative choice. So there's a lot of other toys that you can play with here. So what example if we make compliance reduced? And so we make it so that the industry doesn't really pay attention to you unless your recommendations are really bad, and you get even more massive, even longer period regulatory oscillations. So compliance is important. Regulation doesn't work without compliance, and so you might need to increase enforcement to increase your compliance. So there's a lot of different thought models we can build on top of this. So that's, in general, how we work with a fishery model. And one of the lessons that I want you to take from this is that to put something under regulation in a policy, that is to put it in a balancing feedback loop. And we know that balancing feedback loops, when there are delays, mean that you have an opportunity for oscillations to occur. And so regulation for sustainability may actually cause fluctuations in your variables. And so if fluctuations look bad to you, then you might say, oh, this is a bad outcome. But the alternative, if you got rid of regulation, might be no fluctuations, but it might be a collapse of your natural resource. So if you really want to milk your natural resource for all it's worth, you're pretty much, and you kind of at least have some idea that you've done it in a sustainable way, you may be stuck with fluctuations. But if you want to get rid of the fluctuations and be sustainable, you're going to have to give yourself some margins, which means setting your target harvest rates to be maybe a little less than they could be, because you're going to give yourself a little bit of margins and maybe reduce the opportunities for these massive fluctuations, because nobody likes fluctuations because it's hard to plan. All right, so normally I would ask for questions here. If you do have any questions, feel free to send me an email. Otherwise, this is right out of the chapter. And so hopefully that'll help you when you look back on the chapter and give you some opportunity for clarifications there.